Hey, hi guys. Today we will go through neural networks in continuation to yesterday's discussion that we had. Yesterday we majorly looked at optimizers. We looked at equation and how neural networks equations are formed on what really happens. I think anybody can calculate it as simple as that. Right? X1 goes through different layers and finally it becomes Y. In between different layers, the X1, X2, X3 are transforming, are put into different equations, right? That's the whole concept. So instead of putting it in one equation, we are splitting it, breaking down, and putting into multiple equations, and we are using different weights for different one. So I wrote a blog in which I was actually mentioning saying neural networks is nothing but you're drawing multiple linear equations on top of each other, and then you are achieving. So what happens is if you want to get any shape, all you need to do is if you draw multiple lines, those small lines you can actually adjust it into any shape, correct? So some shape like this, let's say this is the shape of the data pattern that you need to recognize, then all you need is the line should be going like this, right? So if your each neuron contributes to identifying each piece part of it, right, smaller piece part of it, then putting them all together, what happens, your whole boundary will be created, correct? So that's the strategy of neural networks. That's the reason you the more complex your neural networks are, the uh, more alignment it gets to different thing. And the key point is if you start off if this are any shape, right, any shape of data that you have, you can, irrespective of the pattern, as long as you know certain pattern, or it could be in any dimensions also, you can always draw a boundary if you're using small bits of lines, correct? Even if something like this is there, then you can actually, if you have small lines that you could draw, multiple lines that you could draw, then you could draw that line in every space, right? So you can adopt to any shape. That's what I'm trying to say. The pattern, if you want to, if this is the pattern in which it is, if you want to draw a straight line, that's a problem. A bigger straight line like this, like this, then not the straight. Even if you have a curve like this, it will not fit into this data, correct? But when you have a smaller lines that you can draw, those smaller lines can fit in anywhere, and you are drawing multiple lines like that, and those can fit in the whole, they can take the whole shape. But whereas a curve or anything else can't take that shape. That's the key concept. I want you guys to understand it. So there is no super intelligence in our in that. I mean, there is intelligence, but I would actually say I will appreciate it is more than intelligence. It is more on we could achieve good things with neural networks and all that. I would say 50% is to the intelligence of people who have come up with these models and stuff. 50% I would say it is actually the compute and memory capabilities that have grown over the period of time. Because if you see the fundamental concept of neural network, it is very close to how it was few decades back. Yeah, so it's the same, but how it evolved now, how did the models become very intelligent? No, there are definitely a lot of optimizations that came in, which actually made the whole calculations easier. People were optimizing things to an extent, saying with the CPU and memory limitations is to deal with huge amount of data and stuff. People are optimizing it to a scale that it, what are the minimal amount of things that are possible. So that's the reason we study so many optimizations, right? So gradient descent, GD of optimizer of all the data, to stochastic GD, which deals with one record at a time, mini batch MB SGD, mini batch stochastic gradient descent, which deals with the small batches of it, like that. Even Adam, if you look at it, it even though it does the best optimization, it excuse me, even it adopts a stochastic model of or the mini batch model in Adam as well. That's what we've studied yesterday. So all of this, if you look at it, it is the focus was always on adapting to the compute available that is there. So uh, but now that the things are changing, we have better compute available, better memory handling capabilities available. The evolution of neural networks is happening, and we are actually able to see the results. Theoretical concept is there, but you are able to see now that the better compute is there. I think we should be stepping in to much more intelligent models than this. See, um, large language models or neural networks and all that stuff are just like I don't want to say put it that way. People might get hurt, but my understanding, I might be wrong. I will correct it if I'm wrong, but it's more brute force kind of stuff where you pick up either all possibilities, or you use smallest possible piece, and then you try to keep them repeat it hundreds of times so that you can take that shape. That is possible by any algorithm or anything. But here the adaptiveness to unknown scenarios by using that formula is the key logic, and that's where you're able to see more intelligence coming onto the table. We'll go more into it when we reach generative AI. We'll dig more deep into how things are working. But this is my understanding on neural networks. Moving forward today, we'll look at primarily. Let me share the screen. So what we have looked at is optimizers. All these optimizations we looked at it. I think we didn't look at when to use what. I mean, we did look at when to use what with the stabler format and stuff. But Adam is the one which is mostly used. Okay, fine. Sorry. We didn't look at list of hyperparameters. So let's go here. What are the list of Yeah. Yeah. So after looking at this, I feel we'll come back to this. First, we'll complete the regularization. Okay. So we'll just do it. Rules of regular techniques and neural networks. I don't think this page will work. It will say I should subscribe or something like that. This guy's again he'll ask for login. What kind of but interesting. There is something on Langchain. Very curious to start off with Langchain, but the articles, and definitely analytics with the articles are very nice. Right. Small comments. Overfitting, underfitting, regularization concept, we have already studied it with respect to linear regularization. So I don't want to repeat the whole thing. I just want to see how regularization is done um, in neural networks concept. See, again, even though it's, as I said, even though it's a neural networks is nothing but multiple neurons put into different layers. Each neuron, what does it do? Each neuron has a linear regression plus an activation function combination. That's what gives you an output, right? So if you boil down to the granularity of regularization, again, the same regularization will be applicable. You can go for L1, L2 regularization, which you have studied in. Um, but one is lasso, another one is gee, forgot the name again. Let's remember it as L1, L2. It's okay. And dropout, early stopping, and more. Models become more robust and better at making accurate predictions on answer. Okay. This concept of underfitting, just overfitting, we have looked at it previously. Training versus just data error. Okay. So the objective is to go here, where the training is also good, the test data adaptation is also good. You can actually bet better at minimizing the error in training data. But the more you get better with training data, the test data will go away. So one part of, we already studied one part of the use case is we don't have a definitive set which gives the complete pattern of the universal data. So we take a part of it and deal with it. So our objective is always not to achieve best performance on training data, but to receive best performance on universal data, which includes the test data as well. So these two combinations should be good. I think the best combination of these two is here. The best of test and best of training is here. This is optimal model complexity. So if you don't have regularization, this is how it will come. This is definitely overfitting because it assumes that the red cross lines are will be only available in these spots, right? But this is training data. Once the test data comes, the red part spots can come anywhere, and definitely this will not align with it. This is purely overfitting to this particular training data. Once the test data comes in, it doesn't really fit in on what is. So now what happened because of adding regulation? So regulation is nothing but you try to optimize it to actually take this line to form this line. But what happens is regularization, we add certain additional value to the cost or loss in a way that you can't go beyond a point, or whatever you do you can't reduce the loss beyond that particular point. So you we are literally stopping you from going to zero. So the objective is to go towards zero, but at the same time you should not go to zero, because if you go to zero, that means you are overfitting. That's the whole concept of regularization. So once we add the regularization terms, what happens is the line that you draw, it would not tend to go that far that it adapts to each and every point. Yeah, this is appropriate fitting. Correct. L1 and L2. So cost function is equal to loss function plus regularization term. The regularization term for L2 is lambda by 2m into sigma w2 square. That is what is the variables. If you look at cost function, it is a cost function, and w's is what we do, and that's why we take a differentiation of cost function with w's, and that's what we use as gradient descent equation and stuff, right? So weights are the changing ones in the cost function. So what we do, those weights itself will multiply with the lambda, we'll add it here. So irrespective of adjusting the weights, even if you increase decrease the weights, those will actually be adjusting the weights will also update the cost. So just by adjusting the weight you can't change the overall cost, because the cost will always get implicated directly and indirectly by w also. So L2 is w square sigma w square, L1 is sigma w. That's all. See, this is the L1 L2. L1 is power 1 of w sum, and L2 is power 2 of w square. L1 L2 is clear. Now dropout. As I said, when you go to this shape, each neuron tries to adopt certain shape, correct, of this pattern. Dropout is primarily saying you remove certain neurons. Okay, so what happens, learning, so this curve and this curve, these all curves are adopted by certain neurons, right? So that is where it overfits. If I randomly remove certain neurons, what happens? Few of those lines will be gone. They could be gone here as well, here, anywhere. But because of those lines not being there, it wouldn't be able to take the exact shape as this one. Agree? So dropout is where it wantedly doesn't want to remove certain lines so that it doesn't take the exact shape of the particular pattern that we are trying to achieve. So that's the dropout logic. So they disable neurons like this. Overall, fun, like by the time you come to the end, it would remove automatically. It will remove certain pieces that are required and stuff. But another question that would come out is, how do you pick up? What is your approach to dropout? Which neuron should you drop off? Yeah, that's a complex thing. Um, we should look at it. We'll study that as well. Iteration has a different set of nodes, and this is okay. Yeah. So see, um, let's study that. This is one of the most interesting types of regulation techniques. It also produces very good results and is considered one of the most frequently and used regulation techniques in the field of deep learning. Correct. To understand dropout, let's say our neural networks is akin in the on shown below. So what does dropout do? At every iteration, it randomly selects some nodes and removes them along with all of their incoming and outgoing connections as shown below. So each iteration has a different set of nodes, and this results in different set of outputs. It can also be thought of an ensemble technique in machine learning. Yeah, ensemble models usually perform better than a single model as they capture more randomness. Similarly, dropout also performs better than a normal neural network model. The probability of choosing how many nodes should be dropped is the hyperparameter of the dropout function. As seen in the image above, dropout can be applied to both the hidden layers as well as the input layer. In certain features can also be stopped. This reason dropout is usually preferred when we have a large neural network structure not to introduce more randomness. So again, Keras is one of the library which has implemented all that we have studied till now, including linear regressions, logistic regressions, regularization, gradient descent optimizers, everything that we discussed. The concept they are programmatically implemented it. They've wrapped it and gave it as a library. So instead of writing the all granularity of the code, we can just call the method. So in this, if you look at this code, uh, sequential, and he would actually call in model is equal to sequential of, and he would call out the layers that is there, that are there, right? And then we can call out in this particular layers, we can call out on what's the dropout uh, rate. You can see we have defined 0.25 as the probability of dropping. We can tune in further for better results using the grid search method. Again, grid search method is something we'll look at it when we look at hyperparameter tuning. I think hyperparameters and hyper tuning can't be covered today. We'll look at it. Data augmentation. Simple way to reduce overfitting is to increase the size of the training data. In machine learning, we were not able to increase the size of training data as the label data was too costly. But now it's, let's consider we are dealing with images in this case. There are few ways of increasing the size of the training data: rotating the image, flipping, scaling, shifting, etc. Yeah, there are techniques in which you can increase the training data by creating the data from the source data itself. So for example, for images, as this said, you can flip the data, you can rotate, scale, whatever. There are different things which you can create the data, and then there are libraries which does that early stopping. That is, if you see that if you run your code, and then if your loss is getting to, let's say you don't have dropout, you don't have regularization, you have the training going on to certain n number of they call it, the iterations will, when we see hyperparameters will study about it, they call epochs, n number of epochs, and your loss is so minimal that it is close to zero. Then you know how many epochs you are reaching there. Then what will do, you reduce that epochs to a certain stage, uh, and that will give you a better result. But let's read it. Early stopping is a kind of cross validation strategy where we keep one part of the training set as a validation set. When we see that the performance on the validation set is getting worse, we immediately stop the training. Okay, so this is a different approach than what I was saying. So it's more a cross validation. In the above image, we will stop training at the dotted lines, since after that our model will start overfitting on the training data. Okay. Here monitor denotes the quantity that needs to be monitored, and value error denotes the validation error. Where do you use patience? Patience has a number of epochs with no further improvement, after which the training will be stopped. For better understanding, let's take a look at the above image again. After the dotted line, each epoch will result in a higher value of validation error. Therefore, 5 epochs after the dotted line, observations is equal to 5, our model will stop because, oh, okay. So he says patience is equal to 5 is here. Sorry, I didn't notice. So from here, 5 epochs, he'll go forward and then he'll stop it here. I don't know why he uses cross validation. It's not cross validation is one technique, but as simple as that, he'll see the he'll see where the number of epochs is going to minimum, and from there he'll work backwards to get at certain value where the error on he'll notice the error on the test result growing for the training result being there, and then he'll try to optimize the value where he needs to stop. Okay, managed data, Keras is okay. Start regularization, that's okay, fine. So those are all the regularization techniques. I think we've covered majority of them, which is clear. But these are ways in which we generate the data. So by whitening, so actual clear images, you distort them and then make them in different color, and still the system should be able to detect those. Is the expectation, which is nice. Because realistically, these are all possible, right? Where other things will come up and stuff. Okay, that's with this thing. We'll wrap up little early today. Hyperparameter tuning is something that we thought of looking at, but we'll possible if we'll cover it tomorrow, or else we'll cover it day after. Hyperparameter tuning. Um, I hope regularization is very clear. So L1, L2 regularization. We looked at the dropout. We looked at adding more additional data. We looked at early stopping. Yeah, that's it. Those are the concepts of regularization in neural networks, and we understood how they would actually help us in reducing the overfitting uh, by reducing the way the pattern recognition is either stopped or few of them are removed, so that in a way that the output will not try to overfit all possible patterns. It will only pick up certain patterns within it, and basing on that it will arrive at an output value. Yeah. Okay, thanks guys, we'll discuss later.